In this session, we're going to discuss Euler and Hamiltonian paths. Specifically, we're going to define what is Euler paths and circuits, Hamilton paths and circuit, and its application. So let's start with Euler paths and circuit. We all know that one application of graph theory is determining path in a road. Okay, so using the concept of graph theory, we could define what will be the traversal of a certain person in a road in a certain location. Okay, if we want to go from this point to another point, okay, we could use graph theory for that. Okay, and this concept basically was used or was adopted during the 18th century. Okay, so one example here is during the 18th century. Okay, so in Kaliningrad, Russia, so they have this um, portion of their land or a portion of their territory wherein they have four sections, which is divided by Bregel River. Okay, and this four section is basically connected a by a bridges by a bridge. Okay, so the total bridges is seven. Okay, so this is section A, section B, section C, and section D, and these are all the bridges connecting this four section. Okay, so using graph theory, we could recreate it using this graph. Okay, so C and A and B and D are your okay are your vertices, are our vertices, and the edges are the bridge or the road is the vertices or is the edges rather. Okay, and during that time people wonder, so if we could go to the different section using all bridges, okay, exactly once, okay, and we could return at the same point. So for example, we start with A, we want to go to B, D, and C using all the bridges, and we return to section A. Okay, so actually this was been solved by Leonard Euler, one of the Swiss mathematician that creates lots of theorem in math, okay, that we use nowadays. Okay, and Leonard Euler basically disproved this notion. So he said that there's no path that will satisfy or um, that will that will give us, or there's no path that will say that we could use all the seven bridges, okay, exactly once to traverse to all section and we end on the same point. There is no path for that. And this logic is basically one of the first theory or theorem that was used in graph theory, and we call it Euler path and circuit. So let's define first what is Euler path. If it's a Euler path, it is a path that chooses every edge in a graph with no repeats. Being a path, it does nor have to return to the starting vertex. So it means when we are traversing, so the start and end could be different. And for Euler path, all vertices should be included on the traversal, and all edges should be used in the traversal, and there will be no repeating of edges during traversal. Okay, so don't forget that. So start and end could be different. All vertices should be included, all edges should be included, and it should only be used one time. Okay, so let's have this graph just to show you how Euler path works. Okay, so let's start with Okay, point D. So vertex D. This will be our start point. So we want to traverse, okay, to the different vertices using Euler path. Okay, so S or star S. Start the vertex. So definitely we need to go to, okay, to C. And then afterwards, we're going to go to B, and then going to A, and then going to C. So by the way, in the junction C or in the vertex C, you have two options. You may go to A or you may go to B. But for my example, I go to B. Okay, so let's check if we have a Euler path. Okay, based on my traversal. So we start with S, or we start with D rather, and based on our traversal, all vertex was included, were included, all edges are included, were included, and we only used all edges one time. So therefore, this is the Euler path. So Euler path, the traversal will be again from D to C to B to A to C. Okay, to use all the edges one time. And another Euler path is D, C, okay, A, B, and then C. So both are example of Euler path of this graph. Okay, now let's move on in discussing Euler circuit. If say Euler circuit, okay, it's almost the same as Euler path actually. The only difference is it should start and end with the same vertex. If we're going to start with B in this example, we're going to end with B. Okay, that's the only difference between Euler path and Euler circuit. Okay, start and end vertex. So let's get a Euler circuit of this graph. So I'm going to start with B. Again, this is my start vertex. So I'm going to go to E. Again, this is just my example, so it's up to you how you're going to traverse as long as you follow the Euler path concept, okay, except for the start and end. Okay, it should be the same. So that will be Euler circuit. Okay, so start with B, go to E, then go to A, then from A, I'm going to go back to B, and then I'm going to go to E again, and then from E, I'm going to go to D, and then D going to C, and then C to B. So when I stop with B, kindly check if all edges were used. Yes, all vertices were included on the traversal. Yes. And did we start and end with the same vertex? Yes. So we end with B vertex. So therefore, this is a Euler circuit that start and ends with the same vertex. Okay, so just to write the path. So we have B, E, A, B, E, D, and C. Okay, so that will be the traversal or the path for the Euler circuit. Okay, so you could traverse in different way, so it's still accepted as long as we follow the rule of or the definition of Euler circuit. Okay, so again, my answer is or my traversal or my my chosen path is one of, okay, of the traversal path for Euler circuit. Okay, so you could have a different simulation or different ways, so it's still acceptable as long as we follow the definition of Euler circuit. Okay, so how do we check if we could get a Euler path or a Euler circuit in our graph? So we have a rule to determine if we have a Euler circuit or Euler path in a given graph. So let's start with Euler path. So graph will contain a Euler path if it contains at most two vertices of odd degree. So what is a degree in vertex? So the number of edges connected to our vertex. So we have degree 0 if we don't have a vertex, degree of 1, okay, degree of 2, degree of 3, and degree of 4. So the number of vertex, so we have a graph, so at most two vertices of odd degree, okay? So maximum of 2 odd degree. So it means, let's suppose we have degree of 3, okay? So at most, we only have 2 vertices that have degree of 3. More than that, we don't have a Euler path, okay? So for example, let's have this. So let's check. So for A, what is the degree? So we have 2. So we have 2. Here for B, we have 2. For C, 1, 2, 3. And how about F? We have 3. So maximum of, don't forget, maximum of odd should be 2. So more than 2, we don't have Euler path. Okay? So let's check letter D. We have 2. Okay, so we have 2 and we have 2. So therefore, since the maximum odd vertex or odd degree rather is 2, we have 2 odd degree. So therefore, we have a Euler path. Okay, so I'm going to start with C. So I'm going to go to F, then E, then D, then C again, go to B, go to A, and then go to F. So as you can see on my traversal, all edges were used and also all vertices were included. So this is the Euler path. So just to write the traversal, so we have C, F, E, D, C, B, then A, and then F. So that will be our path for this example. Okay, another example. So again, let's check first if we could obtain a Euler path. So by determining if we have maximum of 2 odd degree. Okay, so let's start with A. What is the degree of A? 3. How about F? 3. How about B? 3. Since the odd degree is more than 2, therefore no Euler path. So we don't need to do the traversal because of the initial test. Okay, it didn't follow the rule. Okay, to determine if we have a Euler path or not. To have a Euler path rather. Okay, so no Euler path because we have 3 odd degree. Okay, the maximum of odd degree should only be 2. Okay, so don't forget that. So no Euler path for this example. Okay, now let's move on with determining if we have Euler circuit. Okay, so the rule will be all vertices have even degree, no odd degree, just even degree. Okay, so for example, okay, so what will be the degree of B? 2, A, 2, C, 2, 4, CF, 4, D2, E2. So based on this, okay, all degree are even. So therefore, we could create or we could define a Euler circuit based on this graph. Okay, so I'm going to start with C. So again, Euler circuit started ends with the same vertex. So C, go to F, go to E, go to D, go to C, go to F, go to A, go to B, and then go to C. Okay, so I start and end with C. All vertex were included in the traversal. All edges were used one time, and all edges were included. So therefore, we have a Euler circuit. Okay, so that will be the traversal. Another example, let's check if we could have or we could obtain a Euler circuit. Okay, so let's check for letter B. What is the degree? 2. How about C? 1, 2, 3. So we have 3. So we could stop. Since we have an odd degree, therefore no Euler circuit because of this third degree, degree 3. Okay. Again, to have a Euler circuit, we should only have even, okay, even degree. Okay, so that's Euler circuit. Okay, so don't forget all those rules to define a Euler circuit and a Euler path. So these are some application of Euler path and circuit. So they definitely we could use it to define path or how we're going to traverse in a neighborhood or in a transportation network. Okay, or you could also use in a communication network. Okay, and also we could also use it for circuit design. Okay, network multicasting, and even in molecular biology. Okay, so we have lots of application for Euler path and circuit, okay, in real life scenario. So now let's move on with Hamilton path and circuit. So basically the difference between Hamilton path, circuit, and Euler path and circuit is in Hamilton path and circuit, it doesn't need to use all edges. That's it. That's the only difference between Hamilton and Euler. As long as you included all vertex in the traversal, okay, it will be considered as Hamilton path and circuit. Okay, so the only difference again, you may not, you could, we could, not all edges could be can be used. Not all edges in Hamilton, as long as we could traverse to all edges, to all vertices rather. Okay, using edges one time. We don't need to use all edges in Hamilton, as long as we could traverse to all vertex. Okay, using only once. Okay, the edge. So we could create a Hamilton path. Okay, again, the difference between Hamilton path and Euler is using the edges. Euler need all edges. Hamilton doesn't need all the edges. Okay, as long as we could traverse to all vertex, it's okay with Hamilton pattern circuit. Okay, so for example, so we have graph 1. So the Hamilton path would be, again, start and end could be different. Okay, so we don't need to use all edges in traversing. So let's start with A. So I could go to E, go to D, go to C, and then go to B. Did I traverse to all vertex? Yes. Not all edges were used. It's okay with Hamilton. Okay, but I already traversed to all vertex, so therefore this is considered as Hamilton path. And if you want to get the Hamilton circuit, just go back to A. That will be the Hamilton circuit. Start and end should be the same. Okay, so let's have G2. Okay, so can we have a Hamilton path? Yes. So let's start with A. So go to B, go to D, go to C. So did I include all vertex? Yes. Okay. Did I use the edges once? Yes. Okay. And again, in Hamilton, we don't need to use all edges in traversal. Okay, so same example, can we get a Hamilton circuit? Probably no, because we cannot go back to A, okay, since we only have one path. Okay, so we cannot get a Hamilton circuit for G2. How about G3? What will be the Hamilton path? Okay, so probably we cannot go traverse to all vertex. Why? So for example, we start with A, go to B, and go to C. So if I'm going to go to D, there's no way to go back since I already used this path. Okay, if I'm going to go to E, G, how am I going to go to this? How am I going to use this edge to go to F? There's no way. So therefore, I don't have a Hamilton path for G3. Most likely, if we don't have a Hamilton path, most likely we don't have a Hamilton circuit. Okay, so that is Hamilton path and Hamilton circuit. So what is the application of Hamilton path? It's basically for traveler, for salesperson, if they want to go to different houses, okay, in less number of paths or less number of roads, okay, so they could use Hamilton path for that. And also one application of Hamilton path is on the grade code, in determining the grade code. So I know you're familiar with it. Okay, so that's it. This is my last slide for this video lecture. So if you have some question, kindly send me a message, please, send me a message about this topic. Okay, thank you and see you to our next video lecture.